Japan invested billions of dollars into a train project so futuristic it was designed to redefine travel. Yet, after decades of planning and construction, it still isn't operational. This isn't just another high-speed train. It's a marvel of engineering, promising speeds that make conventional bullet trains look slow, sleek aerodynamic designs that resemble spacecraft more than locomotives, and technology that symbolizes Japan's global reputation for innovation. The stakes are enormous. This project is not only a test of technological prowess, but also a matter of national pride, economic competitiveness, and international influence in the high-speed rail industry. With every delay, the world watches to see whether Japan can truly deliver on a vision that was meant to change the future of transportation forever. The centerpiece of this ambitious vision is the Chuo Shinkansen, a maglev, magnetic levitation line, designed to connect Tokyo to Nagoya initially, with eventual expansion to Osaka. Unlike traditional bullet trains, the Chuo Shinkansen levitates above the tracks using superconducting magnets, allowing it to reach speeds of up to 500 kilometers per hour, 310 miles per hour, with minimal friction. Despite its futuristic promise, the project has faced multiple delays, with construction and testing pushing back the original opening date and costs ballooning into tens of billions of dollars. Maglev technology is still being refined, with rigorous safety checks and test runs ongoing, keeping the line from carrying paying passengers. Globally, the project is a benchmark for next-generation rail technology, setting standards that other countries eye closely as they consider their own ultra-high-speed transportation systems. The Chuo Shinkansen was conceived as a game-changer for domestic travel in Japan, promising to drastically reduce journey times and revolutionize commuting between major cities. On the initial Tokyo to Nagoya route, the train is expected to cover roughly 286 kilometers in just 40 minutes, compared to about 90 minutes on the fastest conventional Shinkansen. When extended to Osaka, travel between Tokyo and Osaka could be slashed from the current 2.5 hours to just about 67 minutes, effectively redefining the concept of regional connectivity. Beyond speed, the project embodies Japan's ambition to showcase cutting-edge technology on a global stage. The maglev system uses superconducting magnets to lift and propel the train without direct contact with the track, eliminating friction and allowing unprecedented acceleration and stability. The train's design also prioritizes passenger comfort, with smooth rides even at extreme speeds and state-of-the-art safety systems to handle emergencies or natural disasters such as earthquakes. Economically, the line aims to stimulate growth by connecting business hubs more efficiently, encouraging development in regional cities along the route, and maintaining Japan's position as a leader in transportation innovation. In short, the Chuo Shinkansen is not just a train. It's a symbol of technological ambition, national pride, and the future of high-speed rail worldwide. The Chuo Shinkansen relies on magnetic levitation, or maglev, technology, which is at the heart of its speed and efficiency. Instead of wheels on rails, the train floats above the track using superconducting magnets, which both lift and propel the train. This eliminates friction, allowing it to reach speeds of up to 500 kilometers per hour, 310 miles per hour, far faster than conventional bullet trains. The tracks themselves are highly precise, built with strict tolerances to ensure stability and smooth operation at extreme speeds. Tunnels and elevated sections, especially through mountainous terrain between Tokyo and Nagoya, have required extraordinary engineering, including some of the longest and deepest railway tunnels in Japan, carved through solid rock with advanced tunneling machines. Energy efficiency is another key component. Maglev trains consume electricity efficiently relative to their speed, and the line incorporates state-of-the-art regenerative braking, which captures energy when the train slows and feeds it back into the system. Safety systems are equally advanced. Earthquake sensors and automated emergency braking are integrated to detect and respond to tremors or other hazards within milliseconds. Noise and vibration are managed through aerodynamic design, shock absorption in the train cars, and carefully engineered track support. The combination of tunnel engineering, magnetic levitation, energy optimization, and safety innovation makes the Chuo Shinkansen a technical marvel, but also one of the most complex rail projects ever attempted. Despite its ambitious vision, the Chuo Shinkansen has faced a series of technical, environmental, and financial challenges that have repeatedly delayed its opening. One of the biggest hurdles is the complexity of maglev technology itself. Floating a train at 500 kilometers per hour requires absolute precision in track alignment, magnet calibration, and power delivery. Any minor error could compromise safety or performance. Tunnel construction through Japan's mountainous terrain has proven especially difficult, with hundreds of kilometers of rock requiring painstaking excavation, reinforcement, and seismic proofing. Environmental and regulatory concerns have also slowed progress. Tunneling and land acquisition often intersect with protected ecosystems and densely populated areas, requiring extensive environmental assessments, compensation for affected communities, and rerouting of some sections. Earthquake risk adds another layer of complexity, as engineers must ensure the maglev system remains safe and operable even during significant seismic events. Financial pressures have compounded these challenges. Initial budgets were quickly exceeded, with costs ballooning into the tens of billions of dollars, drawing public scrutiny and criticism over whether the project justifies the expense. Each delay and technical revision pushes back revenue generation, creating additional economic tension. Taken together, these technical, environmental, and financial hurdles highlight why such groundbreaking engineering projects often take decades to realize, even in a country known for efficiency and precision like Japan. The Chuo Shinkansen is more than just a technological marvel. It is also a major economic and social investment. Economically, the project has created thousands of jobs in construction, engineering, and technology sectors, from tunnel excavation to high-precision electronics for maglev systems. Once operational, it is expected to boost regional economies by dramatically reducing travel times, encouraging business development in cities like Nagoya and Osaka, and making long-distance commuting more feasible. The faster, more reliable transport links can also stimulate tourism, as travelers can move between cities in a fraction of the time and support industries reliant on just-in-time logistics. Socially, the project is a source of national pride and international prestige. Japan has long been synonymous with high-speed rail, and the Chuo Shinkansen aims to extend that reputation to the cutting-edge world of maglev technology. The train also exemplifies Japan's commitment to innovative infrastructure, sustainable energy use, and technological leadership. However, there are social challenges, including public scrutiny over ballooning costs, disruption during construction, and debates over whether the speed and convenience justify the enormous financial outlay. Still, the train's promise of connecting cities faster than ever before, stimulating economic activity, and showcasing Japan's engineering prowess makes it a high-stakes investment with both tangible and symbolic value. As of now, the Chuo Shinkansen is in an advanced testing and construction phase, with sections of the track completed and high-speed test runs ongoing. The Tokyo to Nagoya segment, which forms the first operational phase, is expected to open in the late 2020s, though this timeline has been repeatedly revised due to technical challenges and delays. Tunnels through the mountains are nearing completion, and stations in major cities are being outfitted with the necessary infrastructure to support maglev operations. Extensive testing ensures that every aspect, from superconducting magnets to emergency braking systems, meets the highest safety standards. Looking ahead, the line's extension to Osaka is planned, which will make the Chuo Shinkansen a backbone of Japan's high-speed rail network, connecting three of the country's most important urban centers in record time. Globally, this project serves as a case study for other nations considering maglev systems, including China, South Korea, and the United States, highlighting both the potential and the challenges of next-generation rail technology. While delays and cost overruns have drawn criticism, Japan's meticulous approach demonstrates the importance of precision, safety, and innovation when attempting to operate at the forefront of engineering. If successful, the Chuo Shinkansen will not only transform domestic travel, but also set a new benchmark for high-speed rail worldwide. The Chuo Shinkansen embodies Japan's ambition to push the boundaries of transportation technology. Once operational, it promises to shrink distances between Tokyo, Nagoya, and Osaka, cut travel times dramatically, and provide a glimpse into the future of high-speed rail worldwide. It is a testament to human ingenuity, showcasing how magnetic levitation, advanced engineering, and meticulous planning can come together to create something truly revolutionary. Yet the project also raises important questions. Can Japan deliver on its promise despite decades of delays and ballooning costs? Will the technology prove reliable and scalable enough to inspire similar projects around the globe? And can the social and economic benefits outweigh the enormous investment required to make this vision a reality? Ultimately, the Chuo Shinkansen is more than a train. It is a symbol of ambition, persistence, and the high stakes of innovation, reminding the world that building the future sometimes requires patience, resilience, and an unwavering commitment to excellence.